Hey everyone, and welcome. Have you ever really stopped to think about what the word pure actually means? We see it on food labels all the time, right? But as we're about to find out, what we think of as pure and what science considers pure are two very different things. Let's get into it.
So just think about that carton of milk in your fridge. The label probably says something like 100% pure milk. To us, that means it's fresh, right? Nothing weird has been added. But if you ask a scientist, they'll tell you that milk is, well, not pure at all. It's actually a super complex mixture. So what gives? Okay, here's the big difference right here. On the left, that's our everyday definition of pure. No additives, no funny business. But on the right, that's the scientific one, and it's way more strict. It means a substance is made of only one type of particle. That's it. So milk, which is a jumble of water, fats, proteins, and sugars, is definitely a mixture in a science lab. This whole idea of pure versus mixture isn't just a fun little fact. It's actually the key to how scientists organize and understand the entire world of matter. Think of it as the first big split in the family tree of, well, everything. Yep, pretty much every single thing in the universe can be sorted into one of these two big buckets. Pure substances, which are the fundamental building blocks, or mixtures, which is what you get when you jumble different things together. This simple split is going to be our roadmap for this whole explainer. So first up, let's explore that first bucket, the world of pure substances. These are the elements and compounds that are really the foundation of all of chemistry. Each one has its own unique, unchangeable identity. Imagine a giant stadium where every single person is an identical twin. That's kind of what a pure substance is like. Whether it's atoms or molecules, every single little particle is exactly the same as the next one. So, in a glass of truly pure water, it's just H2O molecules all the way down. So how can you be a chemistry detective and spot a pure substance? It's easy. Just remember the code, CID. C is for consistent properties. That means its boiling point, its color, those things are always the same. I is for inseparable, meaning you can't just filter it apart. And D is for definite composition. Its chemical recipe is totally set in stone. Now, even within this pure family, there are two different types. You've got elements, which are kind of the ultimate loners of the chemistry world. And then you have compounds, which is what happens when different elements decide to team up and bond together. Elements are basically the Lego bricks of the entire universe. You can build anything with them, but you can't break the bricks themselves into anything smaller, at least not with chemical reactions. They are as basic as it gets. Now, a whole bunch of elements are metals, and they share some really amazing properties. Here's another fun code for you. SDM. S stands for sonorous, which means they make a ringing sound when you hit them. D is for ductile, meaning you can stretch them into thin wires. And M is for malleable, so you can hammer them into thin sheets without them breaking. Okay, so what happens when those elemental Legos snap together? Well, then you get a compound. But there are rules. The elements have to combine chemically in a very specific, fixed ratio. When they do, they create a brand new substance with a whole new identity. And this is where chemistry gets really mind-blowing. Okay, get this. Take hydrogen, a gas that's super flammable. Then take oxygen, the gas that fire needs to burn. You combine them chemically in the right way, and what do you get? Water. The very thing we use to put out fires. It's incredible. Compounds can have properties that are totally different from the elements that made them. So that's the whole world of pure substances. But what about, well, everything else? That's where we get into that second big bucket, mixtures. A mixture is a lot like a fruit salad. You can throw in a handful of blueberries and a bunch of strawberries, or a little of each. The proportion doesn't matter. And at the end of the day, they're all just individual fruits hanging out in the same bowl. No chemical reaction, just a physical mashup. This chart really lays it all out, doesn't it? Just look at the key differences. Compounds are a result of a chemical change, while mixtures are just physically mixed. That basic difference changes everything, from their proportions to their properties to how you can take them apart again. But hold on, not all mixtures look the same. In a homogeneous mixture, everything is blended together so perfectly that you can't see the individual parts, like sugar dissolved in your coffee. But in a heterogeneous mixture, you can totally see all the different bits and pieces, like sand and water swirled together. Ever wonder where that sugar actually goes when you stir it into your tea? It forms what's called a solution. That's a type of homogeneous mixture where the particles are so incredibly tiny that they dissolve completely and seem to just disappear. Then we get to colloids. Here, the particles are a little bigger. They're big enough to stay suspended in the liquid. They won't settle down to the bottom. And hey, remember our old friend milk? Milk is a perfect example of a colloid. These suspended particles are also just big enough to scatter light, and we'll come back to that in a second. And on the largest end of the scale, we've got suspensions. Think of muddy water. The particles are so big and heavy that if you just let it sit, gravity will eventually pull them all down to the bottom, separating the mixture out for you. Okay, remember how I said colloids can scatter light? Well, that cool phenomenon has a name. It's called the Tyndall effect. It is exactly why you can see the beams from your car's headlights in the fog. The light bounces off all those tiny water droplets, making the beam visible. This doesn't happen with solutions, by the way, because their particles are just way too small. So we've sorted matter into pure substances and mixtures. But how do these things actually transform? This leads us to one of the most important ideas in all of science: the difference between physical and chemical changes. So a physical change is like getting a haircut or changing your clothes. You might look different, but you're still you. When ice melts, it becomes water, but it's still H2O. A chemical change, though, that's a total transformation. When you burn a log in a fire, you get ash and smoke. You are never, ever getting that log back. A new substance has been formed. All right, let's wrap this all up with a little puzzle. Think about a burning candle. What is actually going on there? Are we looking at a physical change, a chemical change, or maybe something else?
And the answer is, it's both. How cool is that? The wax melting and dripping down the side, that's a physical change. It's just going from solid wax to liquid wax. But the flame itself, the burning wick, that is a chemical change as the wax is transformed into light and heat. It's the perfect everyday example of how all these big scientific ideas are constantly happening all around us.